Good morning, everyone. I apologize in advance if you are hearing some background noise today. It's our air conditioner here. It's unusually loud, but I hope it's not going to be a problem. So this week, I want to speak with you about a really interesting approach that is about statically analyzing software product lines. And in 2014, we had a paper with a bold title, Analyzing Software Product Lines in Minutes instead of Years. And we submitted this to PLDI, which is one of the top conferences in our field. And we did get very positive reviews, but one of the reviewers said, okay, it's a very bold title, but in the end, it actually holds up. So we were really able to bring down analysis times of software product lines from something that would have taken several years to compute to something that now works within minutes. And that was very interesting work in a very international team. So here are some colleagues of mine who worked together on this with me, Mira Mezzini from Darmstadt, but also colleagues here from Brazil, and Klaus Brabrand from ITU Copenhagen. And if you see me back there, that's actually myself. So we actually met, among other things, at a workshop in Darkstuhl back then. And yeah, that's also when we worked on this project and got this going. So what is this all about? Let me briefly recap IFDS and IDE. I've talked extensively about this in DECA 1, so if you want to look this up, feel free to do so. All the videos are available online. I will here only recap the basics. So in IFDS, if you remember, we were basically computing these different path edges here that summarize intermediate flows, basically from one statement to the other, in particular from the entry point of a certain procedure to a given statement. And then when we have path edges that span the entire procedure, they basically form our procedure summaries, right? And we saw that this really works for problems that are distributive, so where the merge operator distributes over the flow functions. And in IFDS, we also had this restriction that there's only a single merge operator that you can use, namely set union. And then we also discussed IDE, which is an extension to IFDS that computes context-dependent information through functions annotated at exploded supergraph edges. So instead of path edges, instead of path edges, we now have jump functions, and these basically can compute these side effects. Also, these functions need to be distributive, but they can actually work on infinite domains. So in particular, we saw that this can be more efficient than IFDS because if you have large domains, but you put them into your value domain L and not in the regular domain D that you use to compute the nodes of the graph, then you can solve very large problems in IDE and even problems with an infinite domain, such as constant propagation, or at least linear constant propagation, for instance. And if you remember, I showed you this example here, for instance, right, where we have several calls to an increment function. And the important point about IDE was that you can now annotate this edge here in particular that actually increments the value with the increment function itself, so that we don't have to store extensional summaries that basically tell you, okay, if you give me a 0, I give you a 1. If you give me a 1, I give you a 2, and so on, right? So here we have this compact intentional summary that IDE computes. And I'm telling you this because IFDS and IDE, they're going to play very essential roles in the approach that I'm discussing this week. So I told you we basically wanted to speed up the analysis of software product lines. I bet many of you don't know this term in the first place. So what is a software product line at all? So think of product lines as the following. You can have individual elements or components that can be composed in many different ways, and that basically allows you to generate all of these different variants, right? So, for instance, you can think of all these different Lego mannequins here, which you can actually compose out of these individual parts here. And what you can briefly or quickly comprehend is that if you have such a number of individual components and they can be freely combined, then you can have an exponential number of different software products or products in general, right? But what we are going to be talking about software products. You also see that not each module can be combined with everything else, right? So there might be some constraint. So, it's not fully exponential, but it's exponential, at least in the worst case. And this can be constrained by a so-called feature model. So for instance, a feature model here that can be read as follows. So this would be saying a Lego mannequin can optionally have a headpiece, and this then has to be a helmet or a hat and not both, right? So this is actually an alternative, right? So an exclusive or, you could say. Then it can also optionally have several items like a brush or a phone. It has to have a hat and it has to have a shirt, for instance, right? So this is how you can read these kinds of feature models. Ultimately, such a feature model can be translated into a huge Boolean expression that tells you exactly which kinds of configurations and combinations here are valid and which ones are not. So this is a product line in sort of real world terms, but the same is also important in the case of software, because also in software you can have product lines. For instance, think about device drivers, right? So you can have a company that produces, I don't know, 50 different printers, and they all have very similar software, but it's not exactly the same, right? Because there are some things that need to be configured for every different device. And similar things occur all over the place. For instance, we have also looked at software libraries such as OpenSSL, for instance, very important cryptographic library. That library should run on a number of different platforms, right? And then the question is, which APIs exactly can you call on which platform? And this also needs to be configured. And the thing is that when you do this, things tend to get wrong, right, and go wrong. So, for instance, there was a very infamous security problem in Mac OS X some years ago. So this was around 2012. So you may have heard of a feature called File Vault. So that's actually a backup program, or not, it's actually a disk encryption program that encrypts your entire hard drive, right? And I mean, one of the key features of encryption is that the secret key should really be kept secret, right? So it should not be given out to anybody. But accidentally, in this particular version that they released here, they had forgotten to disable this debug flag, debug lock. But when this flag was enabled, as it was in this release, then this actually caused the operating system to write your secret password onto the disk itself in plain text. So not even into the encrypted part of, into the encrypted partition. That's obviously as bad as it can get, right? But the problem here was basically that you have a certain configuration in the code. So there was a certain so-called if-def statement in the code that said, okay, if debug lock is enabled, then write this password to the disk. And they did not apparently analyze that particular condition, right? So they may have done a static code analysis, but under the assumption that this debug flag was disabled. So they basically analyzed the wrong code. And then this doesn't really help you. So the point is that in software product lines, you encode certain variability in software. And there are certain simple approaches, such as if-def directives, for instance, that I will also be showing you on the next few slides. But there can also be even more sophisticated approaches than that. But the point is, all these different configurations, they induce a number of different software variants. And traditionally, you would have to analyze all of these. So let me show you an example. Let's assume we have a very simple, obviously contrived product line that looks like this. So we have this program that accesses some secret value. So for instance, such a key, right, and into this variable x. And it's also printing some variable y in the end. And now we want to know, can this value in x actually flow to y? And now if you look at this code base, you will see that it actually depends, right? It depends on which of these features are enabled. So in particular, we here have an if-def-f that guards this line of code. If-def-g guards this line of code, and if-def-h guards this line of code. And what this means is that at compile time, when you actually compile this particular file here, you can select whether any of these features or also a combination of them should be enabled. And any feature that is enabled, those lines are included in the code, but the other ones are not. And now you can take a look at the code and try to figure out for which configurations can a data leak actually occur. So which features have to be enabled and which have to be disabled for secret to flow to y at this point. And traditionally, the only way to really mechanically compute this would have been a so-called product-based analysis that you can see on the following slide. So that means here with 3 different features, you would really have to generate up to 2 to the 3, namely 8 different software products, which you can see here. So 1 product for each configuration, right? So here only F is included, here F and H is included, and here all the features are included. That's obviously an exponential explosion, right? So not good. But this is now, I mean, every single one of these code bases is now a regular C code base, right? So now we have the guarantee that all of these if-defs have been removed. And now we can use a regular off-the-shelf analysis for C programs to find data leaks in the software. And now when you run this, you will find that this will actually detect the data leak for this variant, right? So when only G is enabled, as you see here, then we have a data leak, right? Because X is actually being assigned the secret value. Then this is being forwarded to foo, and foo is now the identity function, and that forwards this to Y. So that's something that you can do, but obviously it can be very expensive because in real-world product lines you can have thousands or usually even millions of products. But the nice thing is, if you can apply such a regular program analysis to a regular program, then you can use regular IFDS-based analysis, right? So like I said, you can use an off-the-shelf data flow analysis, and this is basically an IFDS-based analysis as you would see it for this example program that we have, right? So here we would first have such an edge that unconditionally generates a taint for X, because here X is being tainted by a recognized source. Then here we kill Y, but that's not important, right? So we forward the value in X. That's being then propagated to the parameter the P, that's the formal parameter within foo, and that is being returned to Y. And that's how we can detect this data flow using IFDS. But like I said, in practice, this doesn't really scale, right? Because this product-based approach depends heavily on the number of variants that you have. And so this is a study that I ran back then in 2014, where I actually looked at OpenSSL. And back then already, it had already 391 different if-defs or features, which you can see here, right? So for instance, there's a heavily used feature, C++, that determines whether you're compiling this actually with a C++ compiler or with a C compiler. Then there's also a heavily used feature, OpenSSL FIPS. So FIPS is actually a certified variant of OpenSSL that was certified a while back. And some companies, they have pledged that they will only use certified variants of the code. So they have to enable this flag to get exactly this code and not any other code, right? And a number of these different flags, right? And so if you do the maths, right? So this is about as many features or as many different combinations, right? Or configurations, I should say. And that's really bad, right? So just in comparison, so here you have 10 to the 117. And in the currently observable universe, we have only about 10 to the 80 atoms, right? So even if you could build as many, or if you wanted to build as many machines as they have combinations here in order to run this in parallel, you couldn't do it probably because, we wouldn't even have enough atoms in the universe. So forget about it, right? That's never going to scale. And this also showed in some experiments that we ran. So we did some experiments back then, not actually on C and C++ product lines, but using a prototype that we had for Java. And we implemented 3 different static data flow analysis. So one was computing possible types, runtime types of variables. One was computing reaching definition, so what statements could have defined a certain value that I'm currently looking at. And we were also having an analysis for possibly uninitialized variables. And we applied these through 4 different Java-based product lines. But these were rather small toy examples, I would say, right? So the largest had a few thousand lines of code and also not that many features. So this was still comparatively small. But even if you analyze only these 12 combinations, we saw that these are the analysis times that you get. So in the best case, we had here in the case of Lampiro, the Lampiro application with the possible types analysis, we had an analysis time for all these software products that amounted to 13 seconds. But Lampiro only had some very few configurations as far as I remember. But all the other cases already took several minutes, right? But then we had these really bad cases for GPL and Berkeley DB. So for GPL here, this already took several hours. I think that amounts to about half a day or so of analysis time for all the different products that you have. But for the other ones, it already ran days. And for Berkeley DB, we actually did not finish the analysis because we wanted to publish this paper at some point. So we would have had to run it for years. We know this because we know after how many hours or days the analysis terminated for each individual configuration. And then we basically were able to do a reasonable estimate, right? Because we know by looking at the feature model how many configurations are actually possible for this particular benchmark. And we have a rough estimate of how long the analysis takes for each individual configuration. And then we were able to extrapolate this, right? So it's a rough ballpark value, but the order of magnitude is clear. So it would have taken us several years to analyze this. So clearly, such a product-based analysis approach is not really viable for real-world software product lines. And the whole point of this approach, SPL-Lift, that we developed, is to go away from this and make this faster through a so-called family-based approach. So the general idea here is that we do not want to conduct the analysis product by product, but instead we want to analyze the entire product family, so the entire product line, in one shot by really looking at a single representation of the entire product line at once. And that's what I'm going to explain to you in the next video.